It gives me an error sometimes. Okay, so again, we take it piece by piece. We have to see where this everything is going and then make a decision. Where is this going?
Negative infinity.
Perfect. So now let's see this one. So when x approaches negative infinity or infinity, where is this going? Just this piece.
0.
Yes. How much is 1 minus 0?
1.
Perfect. So then where is this going?
Is 0.
Excellent, because it's natural log 1. Perfect. So the situation we are looking at is 0 times infinity. Remember, 0 times infinity is not a big deal as long as we manipulate the function algebraically. You cannot and you should never touch natural log. Do not try to manipulate natural log. So we have to do something about this without changing the function. So that's not a big deal. Limit as x approaches negative infinity. If I bring this in the denominator as 1 over x, because when I flip it, I get the x back. Okay? So then I have natural log of 1 minus 1 over x. We never try to bring the natural log to the denominator and put negative 1. We will never be able to finish. Oh, sorry. Were you able to see what I did? No, maybe, I don't think you were. Sorry. So first of all, we identify the fact that when x approaches infinity, this approaches negative infinity. Doesn't matter. Infinity or negative infinity is the same thing. This approaches 0. 1 minus 0 is 1, so then natural log 1 approaches 0. So the situation is 0 times infinity. We never bring this to the denominator with a power negative 1. We cannot do that. I mean, we can, but we will never be able to finish, because differentiating a log to a negative power will never go away, right? So what I can do is just bring x to the denominator as 1 over x. Is it the same? Yes, it is. Because when I divide by a fraction, I have to multiply by the multiplicative inverse of the fraction. So this function is the same with this function. But now the numerator approaches 0, and the denominator also 0, because 1 over huge approaches 0. So then I have 0 over 0, which is nice because now I can apply L'Hopital's rule. Remember, L'Hopital's rule is applicable only in 2 situations. It's applicable in 0 over 0 or infinity over infinity. These are the only 2 cases. So I have then, do not drop the limit operator. So you know that from the very beginning of this class, do not drop the limit operator. Do not continue simplifying and differentiating outside of the limit. So please, one more time, do not make that error. It's a big error. I don't want to cut off any points. Please, you know me. I care. I really do. Limit, 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 limit. No limit. Only the last step does not have the limit operator. Do not drop the limit operator anywhere, because it's not true. So if you drop it here, this does not equal this anymore. Please, I'm begging you to pay attention to that. Okay, so where am I? So I'm here with x approaches negative infinity. The top, when I differentiate natural log, I have 1 over that times the inner function prime. So when I differentiate 1, I get 0. When I differentiate 1 over x, we know that this is crucial. When we differentiate 1 over x, we get negative 1 over x squared. This is extremely, extremely important. But I have a minus in front, so it's 1 over x squared over the denominator prime, negative 1 over x squared. So let's do this one more time together. Okay. So when I differentiate with this is easy. When I differentiate natural log of a function, I have 1 over the function times the function prime. So I had 1 over 1 minus x times this prime. But this prime, 1 prime is 0. This prime is negative 1 over x squared, but there is a minus in front, so I have positive. However, I love it. I simplified 1 over x squared from the top with 1 over x squared from the denominator. The only thing I have to worry about is this negative, but I can switch these two and change the sign and not have to worry about that at all. But I have to incorporate it. It cannot go away. So limit as x approaches negative infinity from 1 over x minus 1. And I took care of it. Putting it in front changes the signs here. Same thing. So I wrote 1 over x minus 1. Now I'm in business again, because 1 over x, when x approaches infinity, where does this go?
Zero.
Yes. So what is the limit? This is the last step. This is the only step where the limit operator disappears.
-1.
Yes, which means y equals -1 is the horizontal asymptote at negative infinity. Very good. Well done. So let's look at one more, at least one more of for the power rule, please. Not the power rule, you mean, I mean the indeterminate that are powers. Okay, I will choose 58. It was my turn to choose anyway. X approaches 0 from the right, tangent to x. If we did this problem, we can skip it, or I can let you choose. Did we do this one? I don't remember. Okay, good. So we start from the inside. Where is this going? And then where is this going? Because we need to identify the type of indeterminate case we're facing here. We don't know what it is yet. Anyone, please? What about Mason?
Approaches
Yes.
0.
Yes, good. What about this one?
0.
Good. So the situation is ugly. 0 raised to 0. Good. What do we do in this case? What is the next step?
Take the natural log.
Good. Excellent. Then we apply the limit from natural log y and to the other side. Good. Now again, where is this going? And where is this going?
Zero and 0.
Careful.
Correct.
So don't rush. Let's graph natural log.
Negative infinity.
Yes. Much nicer. You can say, how come? It's still ugly. Yes, but this one requires just an algebraic manipulation. And we just did something very similar. What do you think I'm going to do?
Make x at the denominator.
Exactly. Very good. Limit as x approaches 0 from the right, 1 over x, natural log, tangent to x. And now this is nice. This is infinity, and this is infinity. Any sign, whatever, doesn't matter, right? So we know that this will be, if you want, negative infinity, and 1 over x, when x approaches 0 from the right-hand side, is positive. It doesn't matter. Still infinity over infinity, still nice, because now I can apply L'Hopital's rule. Remember, the limit operator does not disappear till the very last step. Okay, this one is nice. This one is 1 over tangent to x times the inner function prime times the further inner function prime. Okay. Still ugly, but this, as you know, approaches 1. This is 2, so 1 and 2 will go in front as 2. Limit as x approaches 0 from the right. This fraction, oh, I'm going to also put the negative, this negative. This fraction over this fraction, I flip, right? So I get x squared over tangent to x. Nice. Okay. 0 over 0. Still nice. Negative 2. Limit as x approaches 0 from the right. The numerator prime is 2x. The denominator prime is secant squared. 2x times 2. Nice. Because this approaches 1. This is 2. This 2 and this 2 will go away. But this approaches 0. Who cares? 0 times negative 1 is 0. Now I go to the very beginning. This is the only step when the limit operator is gone. So I copy limit as x approaches 0 from the right from natural log y, and I copy the last step. I swap the operators under conditions of continuity. I'm allowed to swap the operators, and I will say natural log of limit as x approaches 0 from the right of what? Tangent to x to power x is 0. So then my question now is, what could this be?
One.
Only 1. Thank you so much. Indeed, that's what it is. So then the limit from tangent to x to raise to power x is 1 when x approaches 0 from the right. Excellent. Okay. Anything else you would like to go back to? You need any help with anything to finish up your work in WebAssign? You need anything else? Anything else? Is there anything that you can think of and say, oh, if I see that, I would like to see another problem? Any topic, any problem, anything. Any problem, any question?
Can we do the fourth question for Newton's method on WebAssign?
Yes, the fourth question for Newton's method in WebAssign. Newton's method, number 4, this one.
Yes.
Is this the same with you, what you have, or you want me to work on your problem?
Yes, it's the same.
Okay, so I have sine x minus x plus 1 equals 0. That's the function. And they want 6. So is that 6 decimal places. Perfect. Good, so first of all, I have to say, number 1, that the function I just created is sine x minus x plus 1. Number 2, f is continuous as a sum difference of continuous functions. Then I have to find an interval where f of the first is whatever and f of the second one is whatever. And then I will have to say by IVT, because it's continuous and it changes sign, there must be a solution between this, and this has to be a 1-unit interval or smaller. Do not put 5 to 10, please. Okay, so I will put in y equals. I'll clear everything, and I put our function that is sine x. Make sure your calculator is in radian mode. Minus x plus 1, please. Okay, so I'll start simple with 0, and then 1, and then 2. That's all I needed. 1 and 2. And f of 1, the function value is positive, and f of 2, the function value is negative. That's all I needed. And I will say, by the intermediate value theorem, there exists a c in the open interval 1, 2 such that f of c is 0. Number 4, I determine f prime of x, which is cosine x minus 1. And in number 5, it's up to you. I like the initial value. It doesn't matter. Cosine 1 radian or cosine 2 radian minus 1 will never be 0. So it doesn't matter. I'm going to start at 1. Number 6, I will create the function x minus sine x minus x plus 1 and over cosine x minus 1. So now I have, make sure that the mode is in radian mode. Yes, it is. I go to y equals. I will insert an x. I will subtract. I will put parentheses. I'll go all the way, put parentheses. And I will divide parentheses again, cosine x minus 1. I get out of there. I go to variables. I go to y equals. I call function y1. I put 1 in it. That's my initial value. I determined, you know that this is above the interval, right? So that should scare us a little bit. Not really. So my x1 is 2.830487722. If the next one does not get closer to the interval 1, 2, then I will worry. Because this is above, right? This is at 3 almost. So I'll say, oops. But if the next one doesn't get closer, then I will worry. In the sense that I probably entered the function incorrectly. Who knows? The method has to converge. it is possible to jump around at the beginning. Okay, so yep. So when I click enter, it should get much closer and definitely in the interval 1, 2. Okay, not there yet, so but it's closer. So 2.049555245. Okay. Okay. Okay, it's getting there. 1.938656127. Okay. 1.934568962. Still not repeating 6 decimal digits yet. 1, 2, 3, 4, 5, 2. Okay, not yet. One more. I bet that this is the last one. The rest will be all the same. 3, 4, 5, 6, 3, 2, 1, 1. And the next one should be identical. It is. So notice that we started with 1, and the solution has to be between 1 and 2. But it is possible that it jumps around, but it has to converge from 283 to 2.0 to 1.9, blah, 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 1.9, and closer. So see, these, normally when I see something like this, then I start worrying. But if it continues to, if it converges, then I'm fine. Now, how do I know if I have an error? Well, something like if x1 is 3, blah, 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 and then x2 is -2, and then x3 is +4, and then x4 is -5.1, then I know something is terribly wrong. Okay? It cannot do that. But although I was expecting 1, 2, it started at 2.83, and I said to myself, if the next one is not getting closer, then I have some error. I have to go back to from square one, and then it converged in 3 more steps. You can say, no, this is step 1, this is step 2, 3, 4, 5, 6. Fine. It's possible that if you start at x, the initial value to be 2, then you will converge faster. Maybe. Is this okay?